course, I don't really need this to make myself heard by you, but since we record these, I'll use this so that the recording device can hear it as well. Welcome to this semester's Keeping Current seminar series. Let me first officially thank the Industrial Partners Association, which provides us with these refreshments. Let me point out that we are no longer wasting plastic on bottles, that we now have a pitcher of water, which means I can finally have water because I don't like drinking water out of plastic bottles. And let me invite all of you to think about what you might want to present. And this is an invitation to, in fact, all of you, undergraduates, graduate students, and faculty, because all of you, and visitors, yes, because all of you have come across something that you find interesting. And if you find it interesting, it might be that no one else has come across it, or that it's not generally known. And people would like to know. For example, what algorithm does an automatic vacuum cleaner take? I have no idea. But maybe you can find out, and maybe you can tell us about it. That sort of thing. So it doesn't have to be your own research, it doesn't have to be deep. But this talk is going to be in a series that Dr. Truszczynski suggested, which is best work. And this is mostly for faculty members, especially gray hairs like me, who look back and say, well, what is the most important thing I ever did? Or what is the most famous thing I did? What am I proudest of? That sort of question. And so what I want to show you is something which I did when I was a graduate student. I was in a course that was a data structures course. This was back in 1972, and the field was fairly young then, and there was no such thing as an undergraduate education in computer science. So graduate students had to learn data structures, and this was my first year, in fact, my first semester of data structures. And I learned more in that semester in all the courses I took than I did in any other semester ever since, because everything was new to me. Well, one assignment, the last assignment, was invent a data structure. We don't give that assignment anymore. And so I did. So that's the background here. And I kind of liked binary trees. They seemed neat to me, and I hadn't ever seen them before that semester. This seems absurd these days. How could a graduate student coming into the department not know about binary trees? But that was then. Question.
Does that mean that all the data structure has been invented?
Yes, they've all been invented, but not everyone has actually seen all of them. There are no new data structures, right? Anyway, so I began by looking at something I knew about. So this is not mine, this is background. Binary trees. And I like to talk about sorted binary trees, although people usually mean sorted. You got a bunch of numbers, real numbers or floating point representations of numbers, and you got a whole bunch of them. And you want to be able to do certain operations quickly. In particular, you want to be able to answer the question, is this number in the set? And you could just make an array of the numbers and look for it, but that's order n. You can do a lot better. And so you pre-process it. And there are many variations, but the variation I'm going to talk about is one where all of the information, all of the actual data points are going to be in the leaves of the tree. So it's an n log n algorithm, and it's an offline algorithm. Offline means you get all the numbers in advance. They're not coming in one by one. You get to see all the numbers. You're going to build a data structure, spend as much time as you need on that, and then you're going to use it many times. And so the way you want to make the tree as balanced as you can. And you don't need anything fancy like red-black trees or AVL trees. Red-black hadn't been invented yet. That was done by Leo Gibas, my office mate, years later. AVL trees did exist already, but they were too complicated to understand. Here, it's much simpler. What you do is you take the median value. Half of the values are on one side, half of them are on the other side. That's going to be your root. And we'll say that that value is the discriminant. Now, if you have an odd number of elements, the median is going to be one of those. Since we're putting all the data in the leaves, if it's equal to or less than, that value will go to the left, otherwise we'll go to the right. We've now divided the world into two pieces, and we've got a root. And then we recursively do both sides. And when we only have 1 point, that's a leaf. That works nicely, and the depth of the tree is going to be log of n, where I use the computer science log. Computer science log is base 2, mathematicians log is base e, engineers log is base 10. We're both engineers and computer scientists, which means we use base 2. So it's order of log n, but it's in fact log n, plus or minus 1. So that's the depth of the tree. The entire construction takes order n log n, and it's really nice. There's a description of how it works, and since I had to calculate the median, and I have to do it at every level, well, I might as well just sort the numbers to begin with. I can do that in order n log n, and that gives me the median for every group as I move down the tree. And I might as well just do that once. All right. Now I can insert into this tree, but it might eventually get unbalanced. So I'm not likely to want to do a lot of insertion if my purpose is to do a lot of searching. But searching is just log n. It's order of log n. And in fact, the average case is going to be log base 2 of n plus or minus 1. So I want to generalize them. And the first generalization you might consider is not the one I'm going to be talking about, but I want to show you that there are all sorts of ways of generalizing. And that's a way of building a new data structure. And so instead of a binary tree, how about a ternary tree? And I sometimes give this as an assignment to build these in my data structures class in 315. And so the idea is internal nodes have 2 discriminants, not 1. Well, maybe 1, but eventually they might get 2 discriminants. And that means they can have up to 3 children. One child, the left child, is all values less than the first discriminant. The middle child are those values which are between the 2 discriminants. And the right child is all values that are they're bigger than the second discriminant. And I've got 2 discriminants then. And I can build these. I'm not going to show you the building method, but these are going to be shallower than binary trees. These are ternary trees, so the depth is log base 3 instead of log base 2. So they're a little bit shallower. They're about 0.63 the depth, which is nice. You don't have to go down as far. That makes it faster, right? Not quite, because every time as you go down, you've got to check against potentially 2 discriminants. So it's twice as expensive at every level down. So 2 times 0.63, 1.26, no, you don't win. Binary trees win over ternary trees. Ternary trees are really neat as an assignment in data structures, but they turn out not to be particularly good as a way of representing data. And once you have ternary trees, you can go down to T-ary trees and make 3-ary, 4-ary, 5-ary. They get worse and worse. But they're all definable, which is nice. And the only reason you might want to do that is for a reason that Ed McCreight, who was the teacher of that course, by the way, had invented the previous year, which is B-trees. Does anyone know why they're called B-trees? How many of you have seen B-trees? Only the professors. It stands for Boeing. He worked at Boeing at that point. So that's why they're B-trees. And the reason they're nice is they're quite high fan out, but what you do is you put all of the leaves into a disk block, which might be 1,000 entries. And so you might have a 1,000-way fan out. So that's something you might want to do if the expense is reading in the disk block, if these are really enormous trees. But we're not going to go there. We're going to generalize a different way. We're going to generalize to a higher dimension, not a higher fan out. And so the idea is, instead of numbers in the real number line, how about numbers in a 2-dimensional plane? Right? Speaking of Boeing and planes, now that's a different kind. So, how can you organize data in the plane? 2-dimensional. And then we'll maybe generalize it to higher, but we'll start with 2. And so here's the idea. Every node is going to discriminate in 4 ways, not 2. There's northeast, northwest, that's for me, northeast, northwest, south, whatever it is, and south, whatever the other one is, right? And so every discriminant, every internal node, has 4 children. Now, some of those children might be empty. Even if you build this in the best possible way, you're not going to get it nicely balanced. You can get it to some extent balanced. So the idea is, here's the construction. Again, it's n log n, and again, it'll be an offline construction. Someone gives me a cluster, a cloud of two-dimensional points, and I want to build something out of it. And so, given a set of two-dimensional values, and I call it VW, V for first dimension and W for the second. All right. If the set is a singleton, fine, that's a leaf, just as it was before. Otherwise, we're going to build a discriminant. Now, I can't get the median, because there's no such thing really as a median of two-dimensional things. But what I can do is independently compute the median in one dimension and the median in the other dimension. That is going to be my discriminant. Some values will fall that way, some this way, some that way, some that way. Now, it'll be more or less nicely distributed. Now, if all the points are in a line like that, my median is going to be somewhere on that line, and there are going to be some empty quadrants. Well, that's just the nature of the beast. You can't do much better than that. But I will have divided at least the remainder into two equal parts. So the depth of this can be as bad as log base 2, whereas I would have expected, I would have hoped for log base 4. If the points are kind of randomly distributed, then I might get closer to a log base 4 depth. But I know that it will be logarithmic in depth. Now, how do I compute those medians quickly? Because I've got all these points, and I want the median in the x direction, and the median in the y direction, and that divides the points, it partitions the points into 4 sets, and for each of those sets, I'm going to have to recursively find medians again. Finding the medians once is not going to work very well. So instead, every time I need this, I'll compute medians again. And what method will I use for finding the median? That's another algorithm, which luckily has been discovered. Well, back when I was in graduate school, no one knew a fast way of doing medians. And then Floyd, another one of my professors, and a few of his students came up with a very nice median building algorithm, which was order n. And then a few years later, Tony Hoare, that's C-A-R Hoare. That's Charles Anthony Richard Hoare, known as Tony from the A, Anthony, came up with something which is called quick select, which is a nice, easy one to describe, and I'm not going to. Look it up. All right, and that's expected order n, not guaranteed, but expected order n. All right, and what you end up with, we'll call it a quad tree, because there are 4 children, we'll call it a quad tree. Well, what good is a quad tree? The fact that it exists and is beautiful, isn't that enough? Here's some pictures. Now, these pictures are wrong. I found it online, I didn't build my own pictures. Look at level 1, the upper left one. All right, that's your swarm of points. Now, level 2, you can see that a discriminant has been found, and it divides the world into 4 points. That's the upper right picture, into 4 quadrants. And each of those quadrants has got about the same number of points. That's nice. And then level 3, you'll see that, let me see if I can point to one of these now. Look at this quadrant over here. It's now been subdivided, and some of its children are empty, and some have points. It did not use my algorithm. Can someone specify what it did do? Yeah, Aiden.
It divided it perfectly into 4 equal areas, but not by medians.
Right. No, who needs these median things? I know where the middle of the volume is, or of the rectangle. I'll just use that as my discriminant. Is it a good idea? Well, it's not going to divide things so nicely. It's still going to be expected order of log n, but it might go a lot deeper than I wanted. And so there is one advantage to doing it this way. Well, 2. One is simpler algorithm, and the other is you can play games and put an extra pointer at every level, a pointer to my neighbor, and because the neighbor is well defined. Your neighbor is always the same size as you, and so you can point to your 4 neighbors at every level. And sometimes for some algorithms that might be nice, instead of having to come up the tree and go back down in the neighborly direction. So there's a reason people might want to do it this way. It's not altogether wrong, it's just not the way I would like to do it. So I say this construction uses a simpler, and I think poorer choice of discriminant. So what's it good for? Well, you can search for a point. Is this point there or not? How do you do that? Well, you start at the top. You compare it to the discriminant in both directions. That tells you which way to go. And you keep walking down the tree until you get to a leaf. Either the leaf is what you're looking for, in which case the answer is yes, and here it is, or the answer is no. That's fairly straightforward. Another is, let's say I've got a region. I want to find all the points within some region. And for simplicity, let's say, I'm calling the region A, I think. Yeah, I've got a region A. And initially, my points are not really bounded at all, minus infinity to positive infinity, in both the x and the y direction. But I want to find all the points in my tree that are actually in that region. So I can use a recursive method. And it's something like this. If A intersect B is null, namely, my region doesn't intersect my universe. I'll call the universe the coverage area of my tree, which begins as infinity, but as I walk down the tree, I start getting borders, and so my universe is smaller and smaller as I walk down the tree. If the region doesn't intersect my universe, fine, there aren't any points that I will report up to my parent. Otherwise, if my universe, B for universe, is entirely within the region A, fine, it's all the points. Return all the points, or just return the whole tree. Someone else can find the points within the tree, just return a pointer to the tree. Otherwise, you recurse, or recur, depending on how you choose, to all four directions and do the same thing again. Very, very straightforward. Now, Jon Bentley was in the same course as I was. He was an undergraduate, and I was a graduate student. And I showed him the quad trees, and he said, hey, these are good for nearest neighbor search. And we worked on that together, and sure enough, let's say someone gives you a point, x, y, and you want to find its nearest neighbor. Well, you walk down the tree looking for it. Now, you might find it, in which case what you find is its nearest neighbor, distance 0. But the chances are when you get down to the bottom, you find some other point. Well, that's a good candidate. That might actually be the nearest neighbor. And you can just stop there and say, this is a near neighbor. Might not be the nearest, but it's a near neighbor. And so going back to this picture that we had, let's say I'm trying to find the nearest neighbor to this point which I'm now pointing to. Well, I walk down the tree, and I'll end up going, well, that's empty, so I go down this way, and I find one of these 2 points, and I find it's this point, okay. That becomes my solution. And in fact, it's pretty close. It might be, in fact, the nearest neighbor, but it might not be. And so what you then have to do is walk back up the tree and say, well, I've got a distance between what I was looking for and what I found. That defines a ball around the point that I'm trying to find its nearest neighbor. Maybe there's another point within that ball which is closer. Now, if that ball intersects one of my other children that I didn't look at, I've got to go down into that other direction, or those other directions. Because in those other directions, I might find a nearest neighbor. But every time I find a nearer neighbor, that contracts the ball. And that means I might not have to look at so many places. And at some point, when I come up far enough, the entire ball is now contained in a child I've already looked at. I don't have to look any further. There are no candidates that are any closer. But if my ball does intersect another direction I haven't yet looked, then I've got to look at that. The actual algorithm is not too hard to write. I've done it many times. And it works very fast. It's got a complexity of order log n, which is the cost actually of going down to find the first candidate. Because strangely enough, if you build this tree nicely the way I want you to, the number of cells you end up having to look at turns out not to be dependent on how many nodes, how many numbers, how many points there are in the whole swarm. If you end up in a region where there are lots of points, you get lots of little rectangles, little squares. If it's a region that's fairly sparse, then you get pretty large squares. And you end up only having to look at a limited number of them. And so that's very nice. The cost then is log n, but it's very weakly log n. It's mostly constant. All right, so that's what I told you about. And you can modify this tree in various ways. One is, you can still insert into it, but as with the binary tree, it will get unbalanced after a while. But if you want to do a few insertions, it's not going to hurt. If you want to do a lot of insertions, it won't hurt, it just will get unbalanced. You don't have to compute distance. I said you look at the distance between the point and the candidate. And the distance in the Euclidean metric, you can use a different metric if you want a different norm. But in the Euclidean norm, you take the square of the difference in one dimension, add it to the square of the distance in the other direction, then you take a square root. You don't need to take the square root, because you're trying to find the minimal distance. That's also the minimal of the square of the distance. So don't even bother to take the square root. You don't need that for this purpose. You don't care what the distance is, and square root is a monotonic. You could use other norms. And another thing is, you don't necessarily want to stop when you get to 1 point. You can stop when you get to 10 points. And you end up with all those 10 points in a leaf. We'll call that leaf a bucket. And we experimented with various values for the size of the bucket. And 10 was, at least in the experiments we ran, anywhere between 8 and 15 was pretty much equivalent for the purposes of the time it took to do nearest neighbor search. So I recommend 10 or so. Now that means whenever you've done a subdivision and you end up with a universe that has 10 or fewer points, then you stop. You call that a bucket. They're not all going to be 10. Some will be smaller. All right. If I can do two-dimensional, I can generalize. Let me generalize now to 2.5 dimensions. No, to 3 dimensions.
Let's see the 5-dimensional version.
Right. Yeah, well, 3 dimensions, it's called an Optree, and people actually use these, but now every point has got 8 children. All right? And again, people are likely to choose a discriminant based on the very center of the current universe, as opposed to the median, which is my favorite way of doing it. So when dimensions 1, well, it's identical to the classical tree. At K2 quad trees, people use these actually quite heavily for image processing, mesh generation, and other purposes. You can look it up on Wikipedia and get a whole list of possibilities. Optrees, which are spelled that way, it's not how we originally spelled it, but they exist, yeah.
You mentioned inserting into it a few times.
Yeah.
When you do that, you're changing the median of everything that.
Yeah, it's not as good anymore as far as balance is concerned.
So when you insert, do you not recompute the median?
You do not recompute.
I see.
And you just put it in the bucket. And if the bucket gets over full, you split the bucket. And that gives you a new level down there. Yeah, that's how you would insert. I wouldn't try to recompute, because that's not necessarily a local operation. All right, for K4, 4-dimensional, well, yeah, mathematically it makes perfectly good sense. But now you've got 2 to the 4th children, 16 children, that's not so bad. After all, Bach had 20-some children. So it's possible, but it gets unwieldy, and it gets more and more unwieldy. And so another suggestion that Jon Bentley came up with is, we can make this binary for any number of dimensions. And we called it a KD tree. And I'm going to show you how that works. The discriminant now is not going to be, if I'm in D dimensions, it's not going to be D values as it was with the quad tree. It's only going to be 2 values. One is going to tell you which of those dimensions you're splitting on. That's just a small integer. And the other is where in that dimension we have found the median. So during the recursive construction, which way do I go? The right way is like this. You find in each of the dimensions of all the points you currently have in your universe, which dimension has the widest spread. That's pretty easy. It's a linear algorithm. And then you choose that direction as the direction you're going to split. And you choose then the median in that direction, which you use quick select and median finding. You use Tony Hoare's method, and that tells you where to split. Then half of the points go this way, half of them go that way, in some direction. And when you go down to the next level, you don't say, okay, I've been in that direction, I'll go to the next dimension. No, you again look at the spread, and you choose that dimension that has got the highest spread. And the reason you do that is you want to make your cells that you end up with, your buckets, as square as possible, as cubical as possible, as opposed to really long and oblong. And it turns out this is the right way to do it. And we can do exactly the same things we could before, searching, finding elements in a region, and finding the nearest neighbor. Same algorithm. Now here's a picture, and let me ask you what's wrong with this picture. So you can see number 1, it's split into 2 halves. Number 2, it's split each of those into independent halves, and it can make different suggestions based on where the median is of its set of points within its universe. That's good. Number 3, each of those has now been subdivided. Number 4 has been subdivided again. What did this construction do that I did not recommend?
Just alternates.
It just alternated which direction to split in. And I do not recommend that. I always suggest that you take that direction with the greatest spread. And an example of where it violated that is, for example, this region here, where it decided to split horizontally, and I might have split that vertically. Okay, so what do you do with really high dimensions? Why would you want that? Well, I use it myself for an optical character recognition program. I've got this hammer, and so everything looks like a nail to me. And so what I do is I take a character that I've photographed, and I divide it into, turns out, 5 by 5 cells, and each of those then has got a density of black. That gives me a number in 25 dimensions. That is then a point in a swarm, and I can take all of the ones that I recognized. Here's an A, here's an A, here's an A. That's 3 points in my space. Here's a B, here's a B, here's a B. It's a point in my space. Now I have an unknown. Find its nearest neighbor. If the nearest neighbor is a B, I'm going to call it a B. Unless the nearest neighbor is so far away that it most likely isn't, in which case I'll call it an unknown. Well, I've got that program, and I can demonstrate it to you. Come to my office, I'll show you. It's good for multiple languages as long as I can separate the individual glyphs. All right, well, this has been used very heavily, and here are some citations. Quadtrees, a data structure for retrieval on composite keys. About 2,500 citations as of yesterday. An algorithm for finding best matches in logarithmic expected time. 3,300 of these. So together, these account for about 60% of all of the citations of my work from the beginning of time on Google Scholar. It's all been downhill since then. Most of my citations are for work, and they still come through. Every day I get a few, a ResearchGate tells me, oh, we found another citation of your work, and I eagerly look. Is it one that I didn't do as a graduate? No, it's another one of those. So that's kind of the moral of the story. It must be my best work, since it's the most highly cited work. Now, in the remaining 1 minute, I want to show you something I did yesterday. This is a sorting method. What sorting method is it?
Insertion sort.
No. That one is Heapsort. You can see the heap in red getting smaller and the sorted stuff in green. And the total cost there. Now I've actually got a demo here I can make demo. This is going to have 4 different methods, and you have to figure out which is which. All right, here's the first method. What is it? Insertion sort. 5 seconds later, it starts another one. What is this graph anyway? It's the x-axis is placed in the array, y-axis is the value at that point. That was selection sort. This, did you see the first phase? It built the heap. Now it's taking things out of the heap, which is in red, and it's taking the minimum value each time and putting it where it belongs. That is heap sort. Now, what's this one? 5 seconds later. That's quicksort. Notice I'm using Lomuto's method for partitioning. And I was using much larger data sets for the n log n methods than I was for the order n methods. So that's what I did yesterday and the day before. But just to show that I'm still somewhat active. So if you have any questions, sorry, it's too late. But maybe there'll be time after Dr. Hayes finishes talking for asking each of us questions. And now we have